All right, very good evening, everybody. Uh, so, welcome to the session on electrical machines. So, yeah, so welcome to. I hope I am audible. Please let me know in the chat box. Somebody, am I audible to everyone? Is the screen visible? Everything is fine, so that we can start the session. Am I audible? Am I audible to everyone? Please let me know. From my end, it looks clear. Is it all right? Yes. Okay. All right. Thank you. So, so welcome to the GATE 2026 Champion Series. So this is a program that we are conducting from last year. So last year for GATE 2025 also we conducted Champion Series, and in 2000 for GATE 2026 also we are conducting this Champion Series. Okay, now coming to the point. So in the last year Champion Series, those who are interested, you can go back to the live sessions. Last year also, in electrical machines, I conducted around 7 lectures of Champion Series. Okay, that is a crisp revision of entire electrical machines. Okay, all the 4 electrical machines I revised. Therefore, this year I don't want to do the same thing because it is already been discussed last year. The subject doesn't change, right? The syllabus doesn't change, the subject doesn't change, the concept doesn't change. So this year what I wanted to do is that I wanted to solve some very important questions related to electrical machines. So one simple point I would like to inform for this particular lecture is I am going to solve most difficult questions. Okay, so those who are waiting for easy questions, you can just switch off this particular lecture. Okay, this lecture I will be discussing moderate to difficult questions only. If you are looking for easy questions, this session is not for you. Okay, also this session will help you to understand up to what depth the questions can be asked in GATE examination. So all the questions I am going to discuss in this lecture are going to be 2 marks questions, and I included objective type, I included numerical answer type, and also I included MSQ type questions. Okay, and the first subject I would like to discuss here is DC machines. Okay, and I would like to do series of these kind of lectures. Okay, series of lectures I'll be conducting. So in this first lecture I'll start this Champion Series GATE 2026 with DC machines. So before starting the session, I wish you all a very happy new year. I hope you'll find success and you'll find good health and everything. Okay, you'll be happy, right? Fine. So let us start the session without wasting the time. I told you I will be discussing moderate to difficult questions. Okay, if you want easy questions, you need not to waste your time in YouTube, right? Okay, so you better learn difficult questions, conceptually rich questions. That is going to help you to learn the subject well. And anybody first time listening DC machines subject, I request you to, no problem, you can switch this live lecture. You please go back to GATE 2025 Champion Series once, where I discussed the theory part of the subject, and then please attend this particular session. If you are a student from Home Institute, no problem. You already attended my lectures, you understand all the theory discussions, we solved numeric number of questions in classroom itself, and this session is going to be helpful. Even other students who already prepared DC machines, already in the revision mode, definitely this session will be helpful. And those who are waiting for theory part to be discussed, this session is not for you because I am going to discuss numerical questions directly. The 2 difficult level questions I am discussing. So therefore, if you don't have knowledge on theory part, that may reduce your confidence. That's why you please go back to the theory part and revise well, and then go to this particular lecture. Okay, so I'm planning to solve around 12 to 13 questions in this session. Okay, a series of lectures I'll be conducting like this. So let's see that. Okay, for every question I'll give 30 seconds to 40 seconds of time, so that you need to read the question properly, understand what is the data given, then only we can answer the questions. Okay, all right, so let's go to the first question. I request all of you, please read this problem. Okay, this is a moderate question, not so difficult, but this can be asked for 2 marks. Okay, So request all of you, please read this problem. I also request everyone keep a calculator with you, that too gate calculator. These are not PYQs. These are not PYQs. These are the questions I prepared on my own. Okay. These are not PYQs. PYQs a long time ago I discussed already. Okay. These are not PYQs. Yeah. So first read this question. A 1500 kilowatt, 550 volt, a 16 pole DC generator runs at 150 revolutions per minute. The armature has 2500 conductors lap connected and the full load copper losses are 25 kilowatt. The useful flux per pole in milliwebers is how much? So we are asked to answer up to 3 decimal places. Okay, in milliwebers I need the flux value. First of all, it is a generator and it was clearly given the power rating of this machine. Okay, so just let me, yeah. See, 1500 kilowatt. First of all, by default, the given power rating is always output power rating or input power rating. Yes, for any machine, be it a generator or motor, the given power rating is always the output power rating. That too, the power rating under full load condition. So therefore, the output power of this machine is equal to 1500 kilowatt. Okay, all right. And the terminal voltage of the machine was 550 volt. This is the next information. And the number of poles are given, 16 pole, and the machine is lap connected. We know when the machine was lap connected, number of parallel paths are equal to number of poles, right? So A is equal to P and the number of poles were 16. That means the number of parallel paths are also 16. And the machine is a generator. As it is a generator, this output power will be electrical power or mechanical power? Electrical power. In case of generator, output power will be electrical power. And it is rotating at 1500 revolutions per minute. So the number of revolutions per minute is, it is not 1500, 150, right? 150 RPM. Okay. And armature has 2500 conductors. Okay. It was given number of conductors are equal to 2500. 2500. And full load copper losses are given. Okay. The copper losses at full load. The copper losses at full load is 25 kilowatt. This is the next information given. And what is a useful flux per pole? We are asked to find out phi. We will generally get the answer in Webers. Later we have to convert it to milliwebers. Okay. This is the given question. So what my aim here is that, first of all, by using this output power, I will try to calculate current generated by the machine. Okay. So once I know the generated current, I can find out the generated EMF of the machine. And later from EMF equation, I will try to find out what is the flux per pole value. Okay. So let me go to the next page. So what is the formula for output power? Output power is equal to VT into IA. I don't know what type of generator it is. I am assuming it is a separately excited generator. Even if you assume a shunt generator also, we know field current is very small in a shunt machine, so you can neglect. Okay. So 1500 kilowatt, that is 10 power 3, is equal to terminal voltage 550 into armature current. So if you solve it, we will get the magnitude of armature current. So I request everybody, please participate, with interest so that you can reply me with your answers. So what will be the value of armature current here? You keep calculator with you. So 1500 kilowatt by 550. Yes, I am getting 2727. 2727.27. So this is the value of armature current. All right. So now the moment I got armature current, I can find out what is the back generated EMF of the machine. It is a DC generator. So what is the formula for EG? We all know EG is equal to Vt plus Ia Ra. Got it? So Vt was 550 plus armature current was 2727.27, but I don't know what is armature resistance value. The resistance value was not given in the question. Even though resistance value was not given, some related information was given, that is copper loss. The copper loss information was given. How much is that? 25 kilowatt. That too at full load. Remember, this current, whatever I found, this is a full load current only. How do I know this is a full load current? Because this power is a full load power. Got it? So as copper loss was given, from that I will try to find out what is the armature resistance. What is the formula for copper loss? Ia square into Ra. This was 25 kilowatt given. You can find out Ra value now. That is 25 kilowatt divided by 2727.27 square. This will give us the armature resistance value. Okay, so generally resistances are very low. So let's see, 25 kilowatt divided by 2727.27 square. I'm getting 0.00336. 0.00336, a very low value. See that? Okay, as it is a very small value, maintain as many digits as possible so that we will get accurate answer. So this is the value of armature resistance. But what's our goal? Our goal is to find out the flux per pole. So now what you do is that replace that armature resistance here, you will get generated EMF. Okay, so therefore it will be 550 plus 2727.27 into what is armature resistance? 0.00336. And to solve it, you will get the generated EMF. Okay, so let's see that. So 2727.27 into 0.00336 plus 550. 559.16. 559.16. This is the generated EMF value. Now, the moment I got generated EMF value, I can find out flux per pole there. What is the formula for generated EMF? In case of DC generator, generated EMF is equal to Z by A into P phi N by 60, correct? Z by A into P phi N by 60. Now we got generated EMF 559.16. 559.16. Yes. Number of conductors already given. How many conductors are there? 2500 conductors. 2500 conductors with 16 parallel paths. Just a moment. Yes, 16 parallel paths. Number of poles were also 16. Flux per pole is the unknown value, that is what we have to calculate. And the speed was given as 150 rpm divided by 60. Now you can see there the only unknown is flux per pole value. You will get the answer in Webers and then convert to milliwebers. Okay. So can somebody please let me know what is the answer for this question? Yes, come on, answer this question. Yeah, I think it is clear. So output power was given. From that I found current value, because remember it is a generator, that's why output power is electrical. If it is a motor, the output power would have been a mechanical power. Okay, it is a generator right now. Clear? Okay. So from the given copper loss, see, while solving copper loss, I took one assumption, that is field copper loss I neglected. Did you understand that? Actually, a generating machine or DC machine will have field copper loss also. That field copper loss I neglected because there is no information in the problem. There is no information in the problem about field copper loss. That's why I am neglecting it. Okay. Yes. That's all. Now, let's move to next question. Okay. This is a quite difficult question, I must say. So you have to think logically to answer this question. So request all of you, please read this problem first. Read the problem. A 200 volt DC generator to have a maximum excitation current of 5 ampere and minimum excitation current of 2.5 ampere. The regulator is to have two steps with equal current changes per step. The following high resistance wires are available: 4 ampere wire of 1 ohm per feet, 3 ampere wire of 1.5 ohm per feet. Which of the following would be the minimum quantity of material to be used? Okay, so I forgot to mention one thing while typing. You please try to understand. This is a DC shunt generator. Okay, that's a correct way of giving the problem. It is a 200 volt DC shunt generator. It is to have a maximum excitation current of 5 ampere and minimum excitation current of 2.5 ampere. So the regulator will have two steps. Regulator in the sense of field regulator, guys. Field regulator to have two steps with equal current changes per step. Okay. So the following high resistance wires are available. 4 ampere wire is available with 1 ohm per feet. 3 ampere wire is also available with 1.5 ohm per feet. Which of the following would be the minimum quantity of material to be used? That is the question. Okay, so how to answer this problem? First of all, it's a shunt generator. Okay, and it has maximum excitation current. You understand, excitation current means field current only. What is the maximum field current? 5 ampere and minimum excitation current of 2.5 ampere. Yes, we all know in a shunt generator, field current formula is equal to terminal voltage divided by field resistance. But here, two field currents are available. One is maximum field current, another one is minimum field current. If I draw the diagram, imagine this is the armature part of the given DC generator. Here we have the field circuit. This is the terminal voltage. Okay. Now tell me, this is the field resistance, for example. This is the field current. Okay. What is the formula for field current? Field current is always equal to Vt divided by Rf. According to this formula, field current will be maximum when this resistance is minimum, correct? And field current will be minimum when the resistance is maximum. What is the maximum field current? 5 ampere. For example, if a field current is equal to 5 ampere, then what is the field resistance? Yes, voltage is given already, right? What is the terminal voltage? 200. The terminal voltage was 200. Field current is 5. That means what is the field resistance? That is a minimum field resistance. Okay, so let me arrange this. Yes. Now see the minimum field resistance. The minimum field resistance will be equal to voltage 200 divided by maximum field current 5. Is it not 40 ohm? Yes. Next, for example, when field current is 2.5 ampere, that is the minimum field current. Minimum field current 2.5. Can I say field current will be minimum only when field resistance is maximum? When field resistance becomes maximum, only when you add extra resistance in series with this field winding. And that extra resistance is nothing but a field regulator. So I have to add some additional resistance here. Okay, so add some extra resistance. That means the circuit diagram will change now. See, this is the field resistance we have. How much we have? We have 40 ohm field resistance. Now some extra resistance was added, that is known as regulator. With how many steps? You see that the regulator used to have 2 steps only. That means the entire external resistance was added in terms of 2 resistances. Okay, for example, if you place the regulator here, let us say that is step number 1, assume this is R1. I can also place the same regulator at step number 2 also, let's say resistance is R2. There are 2 steps in the regulator. Okay, all right. So this is the field resistance strategy. Now tell me, when field current will be minimum, if you place the regulator at step number 1. If I place regulator at step number 1, you see highest resistance is there in the field. Highest resistance means the minimum current will flow. How much is the minimum current? 2.5 ampere. Then could you tell me what is the overall resistance here? Therefore, Rf plus extra 2 resistors are added. This will be equal to Vt by the minimum field current. What is the minimum field current? 200 by 2.5. Is it not 80 ohm? Yes. Already we know what is the field resistance, 40. Therefore, the extra resistance value will be equal to the remaining 40 ohm. Therefore, sum of these 2 resistors is equal to 40. And this extra 40 ohm you have to create using the available wires. What are the wires available? I have 4 ampere wire with 1 ohm per square feet or per feet. Another one 3 ampere wire with 1.5 ohm per feet. But my question here is that what is the minimum amount of material I have to use? There are 4 options given. Which is going to be the correct answer? Minimum amount of material I have to use. Okay, let's see. First of all, I repeat again and again, this is difficult questions discussion, not easy. These are extremely difficult level questions, can be asked for 2 marks. Therefore, those who are very interested to learn the subject till the depth, they must listen to this. Okay, if you are preparing only for state services exams or engineering services exam, this much depth questions will not come. Usually at gate level, that too for 2 marks, some difficult questions may come like this, because regular questions every day you are practicing, right? Some special questions, difficult questions, these kind of sessions can be helpful. Okay, I want my students to utilize the sessions, not like regularly. Okay, sir, I already solved this model, I already solved previous gate question, what is the use of attending one more session? That's why I'm selecting some difficult models. So have some patience and listen carefully so that you can understand. Okay, all right. So now let us see, first I will place the regulator at step number 1, or you place the regulator at step number 2. For example, I place this regulator at step number 2. If I place the regulator at step number 2, what is the resistance offered? Rf plus R2, correct or not? If I place it at step number 1, then the overall resistance would have been Rf plus R2 plus R. But one important question that was given in the problem, what is that resistance? You please read the regulator discussion. The regulator used to have 2 steps with equal current changes for each step. This is the most important information. With equal current changes for each step. That means when I change the regulator from step number 1 to step number 2, the change in the current must be equal. Okay, you got it? So for example, if the regulator is, okay, just a moment. What happened? For example, if a regulator is at step number 1, how much current is flowing? Yes, is it not 2.5 ampere current flowing? 2.5 ampere. For example, if the regulator is placed at this position, how much current will flow? For example, if I place the regulator here, how much? That means indirectly these resistors are not added. If these resistors are not added, how much current will flow here? 5 ampere will flow. So what is the difference between 5 ampere and 2.5 ampere? Is it not 2.5 ampere? That means because of these two resistors, 2.5 ampere current difference will come. Okay, because of two resistors. Then each resistor will make how much current difference? You again divide 2.5 into two parts, 1.25 ampere. Therefore, when, please listen, when the regulator was here, what is the current flowing? 5. If I place the regulator here, the current must increase or decrease now? The current must decrease, right? Why? Because resistance increases. Are you understanding? When the regulator was here, 5 ampere was flowing. But when I increase the step of the regulator, current must decrease because resistance increases. How much current should decrease? 1.25 ampere current should decrease. Now what is the current that must flow here? 1.25 ampere. Okay, now the current is 5 minus 1.25. I repeat, current should decrease. By how much value it has to decrease? 1.25. Therefore, what is this resistance R2 value? Okay, now Rf plus R2 is equal to, remember, resistance is equal to Vt by If only. Vt is equal to 200 by, what is the field current now? It was reduced by 1.25 ampere. Why 1.25? Please understand. Two resistors together reduce the current by 2.5 ampere. But every resistance has to change the current by same value. That means each resistor will reduce the current by 1.25 ampere. Therefore, the current will be 3.75. Already field resistance is 40 plus R2 is equal to, how much is this? Where is my calculator? Yeah. Yeah, let me use calculator. 200 by 3.75. 100 by 3.75. I'm getting 53.33 here. That means what is R2 value is equal to minus 40. 13.33 ohm. Okay, so remember, now this is the diagram. There are two resistors in the regulator. This is R2, this is R1. Right now, the regulator was connected here. Okay, this is 200 volt voltage source. Now, what is the field current flowing? This is RF. What is the field current flowing? 5 minus 1.25, 3.75 ampere was flowing. Okay, and what is R2 value? R2 value must be 13.33 ohm. And what is the current carried by R2? You can see 3.75. To carry 3.75, I have two wires with me. One is 4 ampere wire, another one is 3 ampere wire. Can I use the 3 ampere wire? No. Why? Because the current to be carried is 3.75, more than 3. Therefore, 3 ampere wire cannot be used. Which wire I have to use? 4 ampere wire I have to use. So therefore, R2 is a 4 ampere wire. Definitely 4 ampere wire. And what is the resistance to be offered by R2? 13.33. And it is given in the problem, 4 ampere wire will offer 1 ohm per each feet. If every feet of the wire will offer 1 ohm, 13.33 ohm will be offered by how many feet? 13.33 feet. So 4 ampere wire with 13.33 feet length. Therefore, this R2 is 4 ampere wire with 13.33 feet length. 4 ampere wire with 13.33 feet length. 4 ampere wire with 13.33 feet length. This is wrong, this is wrong. Already two options are eliminated. Therefore, answer will be either of these two. Correct? Now let's see the next observation. What if I change this regulator position to the next one? I thought this is 1, this is 2, right? What if I change regulator position to this position? Overall resistance is increasing or decreasing? Increasing. Therefore, current has to decrease, right? By how much value current will decrease? Another 1.25 ampere. So let's move to the next case where this is RF, this is R2, this is R1. Yes. Where now the regulator is at position number 1. Okay. Therefore, could you tell me what is the current that will flow here? Is it not the minimum current, 2.5 ampere? When you place regulator here, 5 ampere. When I place regulator here, 3.75 ampere. When I place regulator here, another 1.25 ampere will reduce 2.5 ampere. Okay. So therefore, what is RF plus R2 plus R1 is equal to? Eraser is a big problem in digital board. Yes. RF plus R2 plus R1, is it equal to 200 by 2.5? In this, RF is already 40, R2 is already 13.33. I don't know what is R1. This is equal to 80. You can find out R1 value. So how much? 80 minus 40 minus 13.33. 26.67 ohm. 26.67 ohm. Okay, and what is the current carried by this resistance right now? What is the current carried by this resistance? So how much current is flowing? 2.5 ampere is flowing. To carry 2.5 ampere, you can use either 4 ampere wire or 3 ampere wire. Both can carry 2.5 ampere. But in the question they are asking you minimum quality of material to be used. When I say minimum quality, you better go for 3 ampere wire because 3 ampere wire can easily carry 2.5 ampere. Okay, so therefore for R1 I will use 3 ampere wire because 3 ampere wire cost is always less than 4 ampere wire, correct? But with how much length? You please understand, 3 ampere wire will offer 1.5 ohm for each feet. If every feet offers 1.5 ohm, how many feet required to get 26.67? Come on, 1.5 ohm per 1 feet. If it is 10 feet, you will get 1.5 into 10, 15 feet. Sorry, 15 ohm. Like that, to get 26.67, how much wire length is required? 26.67 by 1.5 feet. Yes, how much is 26.67 by 1.5? 17 point. So therefore, 3 ampere wire with 17.78 feet length. So 3 ampere wire with 17.78 feet length. Therefore, option B is correct. Option A is wrong. This is quite a difficult question. While I am solving, it looks like we are understanding it, but initially to get that idea, that is where the difficulty is. Okay? Clear? Okay. These kind of questions will test your knowledge, and these kind of questions will decide the All India ranks generally. Important information in the question is, the regulator is to have 2 steps with equal current changes for each step. That means even though the regulator was changing from one step to another step, the change in the current must be same. The change in the current must be same. Okay. When you don't connect any regulator resistances, the current is 5 ampere. When I connect all the resistors, the current becomes 2.5 ampere. Therefore, the change was another 2.5. That 2.5 I divided into two parts, 1.25, 1.25. That means every resistance addition will reduce the field current by 1.25 ampere. That's what. Okay. When 5 ampere is reduced by 1.25 ampere, then the overall current becomes 3.75. 5 minus 1.25. To carry 3.75 ampere, you need 4 ampere wire. R2 cannot be designed with 3 ampere wire. Okay. You need 4 ampere wire. Then when I change the regulator to R1 position, current becomes 2.5. To carry 2.5, you can use 3 ampere wire. For R1, 3 ampere wire can be used. Okay. This is how we solve the problem. Okay. Are you clear? Right. Next. This is a moderate question. It's an objective type. One option is correct. Please go through this question. I did not take any lecture on per unit systems. In regular class, I will discuss. In regular class, especially in a transformers class, we use it to discuss about per unit systems. I think per unit system you will learn more elaborately in power system subject. In power system subject, there is a dedicated chapter per unit systems. But briefly, we use it to discuss in transformers subject also. But in YouTube, I did not discuss it. Okay. Anyway, go through this problem. In a constant current DC series motor, calculate the value of resistance RD of a diverter in terms of field resistance RF to reduce the exciting current to n times of its full load value. N times of its full load value. This is the question given. Okay. You can pause the lecture and you can try on your own. Okay. You can try on your own. All right. So first of all, it is a series motor. It's a series motor, DC series motor. But one important data that was given is it's a constant current series motor. That means the load connected to the motor is in such a way that it was drawing the same current every time. Okay. So for example, if you draw the equivalent circuit, this is armature part and this is the field resistance. Here we have the terminal voltage. Let's say field resistance is given RF. RF is the field resistance. Assume the current drawn from the source is equal to I ampere. Okay. This is the first case. But in the next case, what happened? A diverter resistance is added. You know, in a series motor, what is meant by diverter resistance? It is the resistance that will divert the field current. And in order to divert the field current, we will connect that diverter resistance in parallel with field winding, right? So in the next case, what we are doing? We are connecting an external resistance in parallel with this field winding. We are calling this external resistance as a diverter resistance. But even though I added this extra resistance, overall current will change or does not change? Does not change. Why? It is given constant current DC series motor. But what will happen now? This entire current will not go through field winding, right? Some current will divert to this extra resistance. Therefore, less current will go to field winding. How much is that current? It is given. In order to reduce the exciting current to n times of its full load value. Now, the current passing through field winding is not I, it is n times of I. Are you understanding? It is to reduce the field current to n times of its full load value. Therefore, it is n into I. That means what is this current? Is it not I minus Ni? Yes or not? Therefore, 1 minus N into I. Are you clear with that? Now, tell me, this winding and this resistance both are in parallel only. Therefore, voltage drop across this resistance and voltage drop across this resistance will be same. What is the voltage drop across this resistance? It is N into I into field resistance Rf. And what is the voltage drop across this resistance? 1 minus N into I into diverter resistance RD. So I will cancel on both sides. You separate diverter resistance. What is the diverter resistance now? N by 1 minus N into field resistance. So this is the diverter resistance value, so that you can reduce the excitation current to N times of its regular value. Okay, so the diverter resistance is equal to N by 1 minus N times of RF. N by 1 minus N times of RF. That means option A is correct. Am I correct? N by 1 minus N times of RF. Correct. Option A is correct. It is reduced by N times or reduced to N times. Please read the problem, everybody. It is not reduced by N times, guys. It is reduced to N times. That means the new field current is N into I. If it is reduced by N times, then it is I by N. That means N is less than 1 here. Definitely current will decrease. Decreased to N times means N is less than 1 here. Okay, N is less than 1. That's a multiplication factor. Yes, all the live lectures will be available, right, in YouTube. Even though you joined late or you did not attended the session, every live lecture will be available in the recorded format in YouTube. You must know more than me, right? You are all tech guys, right? Young people. Okay. Anyway, it's a simple question. Okay. Now, I gave you one MSQ question now. Please look at the screen. MSQ, this is an MSQ question. So one option or more than one option may be correct. Okay. All right. Read the problem. Which of the following expression is the resistance of a direct current armature winding with Z conductors, each having a length of L, including overhang connections, and cross-sectional area S, arranged in A pairs of circuits and P pole pairs, the resistivity of the winding material being rho. Hence write down the expression for simple lap and simple wave winding resistances. Okay, what is the lap winding resistance value and what is the wave winding resistance? That means if the given conductors are designed in lap connected format, then what is the resistance of that winding? If the given windings are designed with wave connected format, then what is the resistance of that winding? Okay, so two questions we have to answer indirectly. All right, so let's note down the information. Which of the following expression is the resistance? We have to find armature resistance indirectly, RA, of a direct connection armature winding. Yes, we have to find out armature resistance with Z conductors. Overall Z conductors are there. Every conductor has a length L. Every conductor length is equal to L. Cross-sectional, hence write down the armature resistance equation. Okay, do you have idea about any issue about OBS Studio? Is it clear, guys? Fine, right? Yeah. Okay. Okay, yeah. Yeah, okay. Yes, so the number of poles are equal to 2 into P. All right, so what is the formula for armature resistance first? In DC machine, what is the formula for armature resistance? Armature resistance is equal to Z into small r by a square. Anybody remember this? Those who studied DC machine subject and practiced the equations, you must remember this. Where Z is total number of conductors, and R is resistance of each conductor. That is resistance of each conductor. And A is number of parallel paths, right? Number of parallel paths. Okay. So already in the given question also, number of conductors are expressed with the letter Z only. Okay, Z is already there. So your duty is to find out the resistance of each conductor first, small r. What is the formula for resistance of any conductor? Rho L by cross-sectional area of the conductor. In the given question, the specific resistance is mentioned with the letter rho only. So no variation. So this is still rho. And the length of each conductor was represented with the letter capital L. So I will replace this small l with capital L. And the cross-sectional area was represented with the letter S. Therefore, cross-sectional area was S. This is the resistance of each conductor. If I replace this resistance in the previous equation, Z into R by A square, therefore armature resistance is equal to Z into, what is the small r? Rho capital L by S by A square, where A is number of parallel paths. Okay. Now, for example, if the given winding is lap connected winding, first question. If it is lap connected, how many parallel paths will be available? Number of parallel paths are equal to number of poles. Am I correct or not? So therefore, resistance of armature winding will be equal to, let me repeat this, Z into rho capital L by S by how many parallel paths are there? Number of poles. In the given question, how many number of poles are there? 2 into P, though don't confuse. P is not number of poles here. P is pole pairs. Therefore, number of poles are 2 times of that. Okay. So therefore, it is 2 into P whole square. Overall answer, Z rho capital L by 2 square, 4 S into P square. Any option like that? Rho Z L by 4 S, it should be P square, right? We got P square. That means we have to find a relation between P and A. What A is representing in the given question? A is representing, please read this. A is representing pairs of circuits. Pairs of circuits means, first of all, armature is a single circuit or number of circuits in parallel? Number of circuits in parallel. How many circuits are there? Let's say this is armature circuit. How many circuits are connected in parallel like this? Can I say, as the machine is a lap connected machine, number of parallel paths, number of circuits are equal to A only. Number of circuits are equal to A. But in the given question, small a is number of circuits or pair of circuits. Pair of circuits. That means each pair, this is one pair. Like that, next to 2 parallel paths, another pair. Next to 2 parallel paths, another pair. Okay, if overall parallel paths are capital A, then how many pair of parallel paths? Is it not A by 2? Total parallel paths are capital A. Then how many pairs? A by 2. So therefore, small a is equal to capital A by 2. Correct or not? Are you understanding? This is where the confusion is in the question. If it is a regular question, they will use number of parallel paths only, but they are not using the word called parallel paths. They are using pair of parallel paths. That means 2 parallel paths equal to 1 pair. Then A parallel paths equal to A by 2 pairs. Therefore, small a is equal to A by 2. Already, what is A? Is it not A number of parallel paths equal to 2P? Yes or not? A is equal to poles. Poles are 2 times of P. Now 2 and 2 will cancel. Indirectly, small a is equal to P. So therefore, in place of P, I can write small a also. Therefore, final answer, Z rho L by 4S into A square. This is the value of armature resistance if the machine is which connected? Lap connected. So, lap connection, we have 2 options. I think first option is correct. Third option is wrong. This is C actually. That's a typing error. Okay. Now I have to answer this question with wave connection also. For example, if the machine is wave connected, how many parallel paths will be available? Number of parallel paths are independent of poles. They are just equal to 2 only. Therefore, resistance of armature winding is Z into R by A square. Z into, what is the resistance of each conductor? We found, right? Rho L by S by A square. That is indirectly 2 square. 2 square is 4. Then the final answer is Z rho L by 4 into S. This is the value of armature resistance when the machine is wave connected. Z rho L by 4 into S. Wave connected, we have two options. Z rho L by 4 into S. That means second option is correct. Here it is given 2S. Actually answer is 4S. The last option is wrong. Therefore, A and B are the correct answers. A and B are the correct answers. Very good, Kavita. You got the correct answer. Okay. A and B are the correct answers. So the only confusion here is that small a that was given in the problem, it is a number of circuits or pair of circuits. Pair of circuits. Armature is not a single circuit. It is a combination of number of parallel paths. If overall 10 parallel paths are there, for example, that means 5 pairs. If capital A parallel paths are there, that means A by 2 pairs. Indirectly A by 2 pairs. Okay. Right. Okay. So when you find the answers, let me know in the chat box. Try to participate in the discussion. Okay. So A and B are the correct answers. It's an MSQ question. All right. So let's move to the next question. This is a question related to losses calculations. Okay. Read the problem. The hysteresis and eddy current losses in a motor running at 1000 revolutions per minute are 250 watt and 100 watt respectively. If the flux remains constant, at what speed will the total iron losses will be halved? At what speed the total iron losses becomes half? That is the question. First of all, iron losses are combination of two types, right? One is hysteresis loss, another one is eddy current loss. In the given question, hysteresis loss was 250, eddy current loss was 100 watt. So initially machine was rotating at 1000 revolutions per minute. Okay. So hysteresis loss was 250, eddy current loss was 100. So at 1000 RPM, hysteresis loss was equal to 250 watt. Eddy current loss was equal to 100 watt. Okay. Then what will be the total iron loss? 250 plus 100. Is it not 350 watt? Therefore, the total iron loss is equal to 350 watt. Now, in the next case, what is the new speed? What is the new speed such that iron loss becomes half of the previous value? See, at what speed the total iron loss becomes half of the previous value? What is the total iron loss in the previous case? 350. That means the new iron loss must be 175. Okay. First of all, iron loss is a combination of the two losses, right? Therefore, the new hysteresis loss plus new eddy current loss, the combination must be equal to 175 watt. First of all, Iron losses depends upon the speed or independent of the speed? Yes, they are definitely dependent on speed. Let's see the formula. What is the formula for hysteresis loss? Hysteresis loss is always proportional to Bm power 1.6 into F, where Bm is the flux density, into frequency. But in the given question, the flux remains constant. That was clearly mentioned. That means, can I write B is a constant value? Therefore, hysteresis loss is only proportional to frequency. And what is the formula for frequency of induced EMF? We know frequency formula in DC generator is equal to Pn by 120, where n is the speed. From this formula, frequency was directly proportional to speed. Hysteresis loss is directly proportional to frequency. That means, can I say hysteresis loss is dependent on speed? Definitely. Correct or not? Therefore, hysteresis loss is directly proportional to speed. N is number of, not number of turns, that is the speed in RPM. If it is directly proportional, can I write first case hysteresis loss by second case hysteresis loss is equal to first case speed by second case speed? What is the hysteresis loss in the first case? 250. 250. Second case hysteresis loss, I don't know. Speed in the first case 1000 RPM. I don't know what is the speed in the second case. In fact, this is the answer I have to find. Yes. Now cross multiply, separate new hysteresis loss. I think 250 will cancel 4 times here. So new hysteresis loss will be equal to N2 by 4 watt. This is the new hysteresis loss value. Correct? Similarly, what is the formula for eddy current loss? I don't have empty page. I will do it here. Eddy current loss. Eddy current loss formula is proportional to Bm square into F square. Once again, flux is a constant value that was given. So eddy current loss is proportional to F square. What is the frequency we found just now? Frequency is directly proportional to speed. Therefore, eddy current loss is directly proportional to square of the speed. So from this, first case eddy current loss by second case eddy current loss is equal to N1 by N2 whole square. What is the eddy current loss in the first case? 200, right? So 100 by new eddy current loss is equal to 1000 by new speed whole square. Okay. Now just to separate, what is the new eddy current loss? Okay. So the new eddy current loss will be equal to, if I cross multiply, N2 square will come. It will be 100 into N2 square divided by 1000 square, that is 1000 into 1000. Correct? 100 will cancel 10 times, it is 10,000. So it is N2 square divided by 10,000. Okay, this is the new eddy current loss. Now you understand what is the new hysteresis loss and new eddy current loss. Can we find out the new iron loss? Just a moment, I don't have additional pages. Let me add few empty pages. We are here. Okay. Okay. See, this is a new eddy current loss, N2 square by 10,000. New hysteresis loss is N2 by 4. Then what is the new iron loss? Therefore, just a minute. Yeah. So therefore, the new iron loss will be equal to new hysteresis loss plus new eddy current loss. What is the new iron loss we found already? 175, right? The overall iron loss should become half. So 175 is equal to new hysteresis loss N2 by 4, new eddy current loss N2 square by 10,000. Okay, are you understanding? You are getting a second order equation now. Okay, just to solve this equation, you will get N2 in RPM. That is the answer. I'm waiting for your answer. Please let me know how much is this. Come on. We are getting a second order equation. That means we will get two solutions. We will get two solutions. Someone said audio and video are not syncing. Is everything all right? From my end, everything looks fine. Okay, let me check in my mobile. It is all right, right? Yes, two solutions you will get, guys. Only one answer will be correct. Probably you'll get one answer with negative sign, right? The equation looks like that. Yeah, anybody please let me know what is the answer. 570 RPM, is it available in the options? Yes, 570 RPM, option A is correct then. Option A is correct. So overall iron loss must become half. So in the first case, the total iron loss is equal to 350 watt. Therefore, in the second case, the new iron loss should become half of that, which is 175. So important data that was given in the problem is flux is constant. If flux is constant, hysteresis loss and eddy current loss will only depend upon frequency, right? Frequency depends upon speed. That is how I found what is the new speed of the motor. So if the speed is reduced to 570 RPM, then your entire iron loss becomes half of the previous value. So the answer is 570 RPM. Correct? Right. Yes, Sharma, I will take one session on induction machines. Don't worry. Okay. This is a pretty much simple question. And this model was there once in ESE exam. And this is important, okay, from the losses concept. All right. Okay. Now let's move to the next one. This is a slightly difficult model, but you will enjoy really answering this question. Those who love electrical machine subject, they'll definitely enjoy this. Okay. So go through this question. Okay. Just read the problem. This is also a question related to losses calculation only. Yeah, read the problem. One of two similar 250 volt shunt machines, A and B, running light. See, running light means indirectly no load condition. The load is very light. You can assume it is no load condition. Running light doesn't mean it is actually glowing a light. Okay, running light in the sense no load condition. One of two similar 250 volt shunt machines, A and B, running light takes 6 ampere when so overall two machines are there, both A and B. They are taking 6 ampere during no load condition. When A is mechanically coupled to B, see, machine A was mechanically coupled to machine B. The input to machine A is 7 ampere when B is unexcited, and 9 ampere when it is separately excited to generate 250 volt. The magnitude of total rotational loss of each machine is how much? The magnitude of total rotational loss of each machine is how much? See, to answer these questions, first everybody should have idea about power losses in DC machine, especially in shunt machine. See, power losses, there are three types of power losses will be available in rotating electrical machines. One is rotational loss. The first one is rotational loss. Next one is shunt field copper loss, and the next one is armature copper loss. But it is clearly given machine is under no load condition. We all know during a no load condition, armature current drawn by motor is very, very small. That's why armature copper loss can be neglected. If armature copper losses are neglected, then what are the only power losses available during no load condition? Rotational loss and shunt field copper loss. Again, this rotational loss is combination of two losses again. What are those two? One is going to be friction loss. Another one is going to be iron loss. So these two combination is what we call it as rotational loss. Got it, guys? And then we have another loss which is known as a shunt field copper loss. Now in the given question, this loss is what we need to calculate. This is the answer we need to calculate. For that, some information was given. So based on the given information, we have to find out this loss and answer to the nearest integer. That is the question. Okay. First of all, how many machines are there? Two machines. Machine A and machine B. Two machines are there. Both are 250 volt machines. Initially, they are under no load condition. Each machine was taking 6 ampere. No load current is equal to 6 ampere. So therefore, first let us check the no load condition. During a no load condition, each machine, what is the supply voltage? 250 volt. What is the no load current drawn by the motor? 6 ampere. Let us write it as I0, no load current, 6 ampere. Therefore, what is the total power drawn at no load? Power drawn at no load, is it not simply voltage into current? 250 into 6. It was 1500 watt. Okay, this is the total power drawn at no load condition. And we all know that during a no load condition, output power will be 0, right? So the entire power drawn by the motor is just equal to power losses. Therefore, this 1500 watt is equal to simply power loss. But I told you that power loss is only one loss or two combination, two losses are there. One is rotational loss, another one is field copper loss. Therefore, out of this 1500, some value is rotational loss and some value is a field copper loss. But we are asked to find out only rotational loss. Okay. For that, some additional information was given. Okay. Let us take it as equation 1. What is additional information given? You see the next information. When machine A is mechanically coupled to machine B, machine A was mechanically coupled to machine B. That means, let's say this is machine A. This was mechanically coupled to machine B. Okay, remember they are shunt machines. Look at the additional information. When machine A is mechanically coupled to machine B, the input to machine A was 7 ampere. This time, the input to machine A was 7 ampere. Machine A, that means supply voltage is how much? 250, right? The input to machine A was 7 ampere. Okay. But B is unexcited. Please understand this. The input to machine A was 7 ampere, but B is unexcited. B is unexcited means its field winding is not excited with any supply. There is no field winding in machine B indirectly. If there is no field winding, flux will be equal to 0 in machine B. If a flux is equal to 0, there won't be any iron losses in machine B. Am I correct or not? Okay. No iron losses in machine B. I repeat my words again. I am going to solve some difficult questions. Okay. This is not so interesting. Quite boring, right? Okay. If the question is very easy, If I give number of conductors, flux per pole, speed, I ask you to calculate EMF equation, or I gave you KVL equation. EG is equal to VT plus IARA. VT is given, IA is given, RA is given, find EG. These kind of questions are very easy. You'll have a lot of interest to solve those questions, but these are difficult models. Okay, so they'll take some time to discuss. So have some patience and listen carefully. Okay, yes. So machine B is unexcited. Unexcited means no iron loss in machine B. No iron loss. No copper loss. Why? Because there is no current in machine B also. Okay, but there is friction loss. Only friction loss. Why friction loss is present? Because machine was rotating, right? Machine B was rotating. Who is rotating machine B? Machine A was rotating it, mechanically coupled. That means in machine B, there is only friction loss. In machine A, which losses will be there? Shunt field copper loss will be there. Next, iron loss will be present because field is excited. Friction loss is also present. Friction loss is also present. Now, this is the power loss in machine A. This is the only power loss in machine B. Therefore, the entire power drawn from the source is a combination of all these losses. Yes or not? Out of that, this loss is already we calculated. What is the copper loss plus, field copper loss plus rotational loss together? How much is this? 1500. This is already 1500. Now, the remaining power is this one. Okay, let us see what is the total input here. 250 into 7, right? I will change the color. So the total power input is equal to 250 into 7. 4 250s is 1000. Is it not 1750? 1750 watt. That is the total power drawn from the source. Remember, the total power drawn from the source is only loss in machine A or only loss in machine 2, overall loss. Both machine losses together, because the two machines are running together. Am I right? Therefore, machine B loss is also drawn from the source only. Okay, so the total loss is equal to 1750. Out of this 1750, 1500 watts is the loss in machine A itself. That means what is the remaining extra power drawn? Earlier, each machine was drawing 15 only, 1500, but now 1750 was drawn. Therefore, what is the extra power drawn? 250. Can I say that 250 is the friction loss in machine B? Therefore, the friction loss is equal to 250 watt. Got it? 250 watt. Now let's see the next case. What is the next case? Once again, machine A is mechanically coupled to machine B. Both are mechanically coupled. First case is 7 ampere was drawn when B is unexcited. Remember, machine B was unexcited. But in the third case, 9 ampere current was drawn when it is separately excited to generate 250 volt. Therefore, machine B is excited this time. That too separately excited. Therefore, third case. So this is machine A, shunt excited. This is 250 volt. Machine A is mechanically coupled to machine B. But remember, machine B is separately excited. Some external DC source is used for machine B. As machine B is excited, there is a flux in machine B. There is a flux in machine B means which losses will be present? Yes, iron loss will be present because the field is excited. Remember, iron loss will depend upon speed only or flux also. Flux also. This time the field is excited, so iron loss will be present. Next, friction loss will be present because rotor is rotating. Don't include copper loss this time. Why? Because the field is shunt excited or separately excited. Separately excited. Therefore, whatever power loss is there in this field winding, it was not drawn from this source. It was separately drawn from another source because it is separately excited. Now, what is the current drawn from the source? See that. The current drawn from the source is 9 ampere this time. The current drawn from the source is 9 ampere. This time the current is 9 ampere. In machine A, which losses are there? There is copper loss, shunt field copper loss, there is iron loss, there is friction loss. All three are present in machine A. How much is this total three combination we already calculated? That is 1500. All right or not? You remember, this is the 1500. This is a combination of all three losses of each machine. Okay. Now, coming to machine B, we already know friction loss is 250. We already calculated here. The friction loss is 250. Now, what is extra unknown? That iron loss. And this entire power loss was drawn from where? From the source only. What is the total power input? The total power input will be equal to, here I am calculating 250 into 9. 250 into 10 is 2500. 9 means 2250 watt. Out of this 2250, 1500 watts is in machine A. 250 is already in friction form. Therefore, how much is iron loss? Out of this 2250, 1500 watts is in machine A itself. Okay, 1500. 250 is the friction loss, 1750. How much is remaining? 500. Therefore, the iron loss is equal to 500. Do you understand this? Therefore, the remaining 500 watt is the iron loss. Now, you understand in each machine what is the friction loss? 250. What is iron loss? 500. Then can you tell me what is the rotational loss of each machine? I told you what is meant by rotational loss. Rotational loss is the combination of friction and iron loss. What is the friction loss in each machine? 250. What is iron loss? 500. So friction loss is 250. Iron loss is 500. What is the total summation is equal to? 750, right? 750. Therefore, the answer for this question is 750 watt. $750 watt. 750 watt. $750 watt. All right. I can also ask you another question. Can you tell me what will be the value of shunt field copper loss of each machine? Can you calculate what will be the shunt field copper loss of each machine? Shunt field copper loss of each machine. Yes, all three losses together it is 1500. Out of that, iron loss is equal to we just calculated 500. Friction loss is 250. 750. Out of 1500, 750 is the rotational loss. That means what is the shunt field copper loss? Remaining 750. Remaining 750 is the shunt field copper loss. Also, there is one more doubt. Sir, in machine B, why I am not adding copper loss? Shunt field copper loss, why I am not adding? Because it was separately excited. It was separately excited. That means it was not drawn from the regular source. A separate source is used. Got it? Right. Clear? Okay. So next one. This is another difficult question. I hope you are able to follow. Okay. Go through this question. A 480 volt 4-pole shunt motor runs at 600 RPM and has 46 slots with 6 conductor per each slot. Wave connected to the commutator. How must the armature and field windings be reconnected to enable the motor to run at its original speed on a 240 volt supply? if the field coils are replaced by others of the same size. Our existing field coils are replaced by some other field coils, so that the condition is the armature should rotate at the same speed even if it is excited from 240 volt. That is the question. Please understand the problem again. It was a 480 volt 4-pole shunt motor, runs at 600 rpm and has 46 slots with 6 conductors for each slot, wave connected. Initially, the motor was wave connected. But look at all the 4 options, the machine is lap connected next time. Okay. And the machine has, overall 480 volt, and it is a 4-pole machine, initially rotating at 600 rpm. Now next time the field winding was modified such that the motor will run at same original speed on a 240 volt supply. So in the initial case, first of all, what is the formula for speed in DC motor? Speed is equal to Vt minus Ia Ra by Ka into phi. If you remember this equation, all right. Otherwise, please understand. This is a speed equation. In this, if you read the entire problem, armature resistance was not given anywhere. As armature resistance was not given, you can neglect this IaRa drop. If IaRa drop was neglected, then speed will be equal to Vt divided by Ka into phi. Okay. Now what the point is, how must the armature and field windings to be reconnected to enable the motor to run at its original speed? The speed must be constant. Indirectly, the speed must be a constant value. Okay. On 240 volt supply, see, first case the voltage was 480. In the next case the voltage was 240. So voltage is a variable quantity. Okay. In the first case, machine is wave connected, but in the second case, machine is lap connected. You can see all the 4 options are lap connected only. That means number of parallel paths will change. And we have to rearrange the field, right? See, 2 field coils are parallel, 1 field coil, like that 4 options are given. So flux is also may be variable. So let us go ahead. How do we answer this particular question? Okay, right. Okay, so what is the equation we got? Omega is equal to Vt by Ka into phi. Anybody remember Ka formula? Normally Ka is constant, but here there is a modification in the construction, right? Initially wave connection, next it was changed to lap connection. As there is a constructional modification, definitely the Ka value will also change. Okay, what is the Ka value? What is Ka? Anybody? I know it will be difficult. Most of the students will not difficult that Ka value. Remember that Ka value because we don't study it much. So the moment you forgot Ka, at least you try to write down our regular equation. What is the regular equations you know? You know back EMF formula, right? What is the back EMF formula? Z by A into P phi N by 60. At least you know this equation, right? Okay. So in this, what are the constant values in the question? Okay, the constant values are, speed is a constant value because it is clearly given we wanted to rotate at same speed again. Speed is constant and number of conductors are constant. I am not changing overall conductors, I am only changing parallel paths. Parallel paths is variable. Poles will be constant, right? Is there any information that number of poles are modifying? No, same 4 poles. I am not changing the number of poles. Okay, so therefore poles will be constant. Flux is variable. I am changing the field connections, therefore flux might be variable. Voltage is variable because the first case 480, next case 240. So I can write down now, voltage is directly proportional to flux in the numerator, number of parallel paths in the denominator, remaining things are constant. So first case voltage divided by second case voltage is equal to first case flux by second case flux into A2 by A1 because parallel paths are inversely proportional. What is the voltage in the first case? 480, second case 240. 480 by 240. I don't know the flux variation. Let's keep it like this. Phi1 by Phi2 into second case parallel paths. First of all, second case, what is the connection? Lap connection. This is second case, the answer. In second case, lap connection, that means number of parallel paths are equal to number of poles. So therefore, A2 was 4. First case, wave connection, so 2. 4 by 2 is equal to 2, right? 480 by 240, this is also 2. Therefore, this 2 and 2 will cancel. That means what? I got Phi2 is equal to Phi1. Therefore, the flux in the second case and the flux in the first case must be same. First case flux and second case flux must be same. That is your answer. So, which of the following options will satisfy this condition? There are 4 options given. In which options Phi2 and Phi1 will be same? Phi2 and Phi1 will be same. In which options Phi2 and Phi1 is going to be same? First of all, can I write phi is nothing but flux? Flux is equal to mmf by reluctance, right? So flux depends upon mmf, field mmf. Flux will depend upon field mmf. Okay. So now let me take the case number 1. It's a shunt machine or series machine? It's a shunt motor, right? So this is the first case, guys. Assume this field winding is having number of turns equal to n. N is the number of turns in field winding. Okay, number of turns n. Assume the field current is equal to IF. Field resistance is equal to RF. Therefore, what is the mmf of the field winding in the first case? Mmf is number of turns into current. So number of turns n. If you are confusing, write nf, number of turns in field winding. Nf into IF. This is the first case. Coming to the next case, that means in second case also mmf must be same. Then only the flux will be same in both cases and that will satisfy the given condition. mmf must be same. Now what is the second case first of all? Any of the 4 options. Any of the 4 options might be second case. Therefore, I will verify each and every option. Look at the first option. In the first option, 1 field coil is used or 2 field coils are used. 2 field coils are used, that too in parallel. Okay. So in the first option, option A, 2 field coils are utilized. Both are connected in parallel. That means this time the mmf is due to 1 winding or 2 windings. 2 windings, guys. NF here, NF here. Both are equal type of windings. Why? Because it is clearly given same size. The field coils are replaced by others of the same size, identical field windings. So this will carry one field current IF, this will carry another field current IF. Therefore, could you tell me what is the new mmf? The new mmf due to first winding, NF into IF. Due to second winding, NF into IF. But remember, this terminal voltage is 240, but this terminal voltage is 480. Everybody has to understand that. Okay. So I can write down here number of turns NF into what is IF, guys? Is it not 480 by resistance only? 480 by field resistance. But here the field current is 240 by field resistance. You can take NF common. It is not 2 NF. Actually 2 NF into IF. What is IF? 240 by RF. What is 2 into 240? Is it not 480? Okay, see, what's your observation here now? See, mmf in the first case, mmf in the second case, both looks equal or unequal? Both looks equal. Both looks equal. So both are equal means your condition is satisfied. Phi2 equal to Phi1. The flux is also equal. Flux is equal, that means the given condition is satisfied. Therefore, option A is definitely the correct answer. Okay. Let us verify. See, the condition is the 2 fluxes must be equal. Fluxes in both cases must be equal. Fluxes will be equal only when mmfs are equal, and I proved it. Yes, mmfs are equal in both cases. Okay. Let us verify the second case also. In the second case, how many field coils are used? Only one field coil. Second option, only one field coil is used. If I use only one field coil, what is the new MMF? Option B. Only one field coil is used. This is 240 volt. This is a field resistance RF. Current is IF. What is the new MMF now? The new MMF is equal to only one field coil, NF, into what is the field current? 240 by RF. But what is the first case MMF? 480 by RF. NF into 480 by RF. But this is the NF into 240 by RF. Therefore, MMFs are not equal. MMFs are not equal means my condition is not satisfied. Therefore, second option is a wrong option. Look at the third option. Two field coils are used, but they are in series. The two field coils are in series. The two field coils are in series this time. Okay. In the third option, option C, I will solve here only. This time, two identical field coils are used, but they are in series. Okay. So both are having resistance RF. Both are having a number of turns in. What is the NF plus NF? Is it not 2 NF? Therefore, what is the MMF in the second case now? Number of turns are 2 NF. What is the current? Current is equal to voltage by resistance only. What is the voltage? 240 by what is the resistance? RF plus RF. Is it not 2 RF? Now 2 will cancel. I am getting NF into 240 by RF. What is the first case MMF? NF into 480 by RF. But here it is NF into 240 by RF. Therefore, the MMFs are equal or unequal? MMFs are unequal. That means the condition was not satisfied. Therefore, third option is also going to be a wrong option. Can you answer the fourth option? In the fourth option, how many coils are used? One coil, but half of the turns are used. Not full turns are not used, only half of the turns are used. Only one coil, but half of the turns. That means, can I say number of turns becomes half? When a number of turns becomes half, resistance also becomes half. Please understand that. The voltage was 240 now. So could you tell me what is the MMF in the second case? Number of turns are half, NF by 2 into what is the current formula? 240 by resistance. 240 by what is the resistance? RF by 2. Once again, 2 goes to numerator, 2 will cancel. I am getting once again NF into 240 by RF. What is the first case MMF? NF into 480 by RF. But second case, NF into 240 by RF. Both MMFs are not equal. Both fluxes are not equal. The condition was not satisfied. This is also a wrong answer. Therefore, what is the only answer that is correct here? First option. Only the first option will be the correct answer. Okay. Only the first option is the correct answer. These kind of questions will come for 2 marks. Remember, the machine has to rotate at the same speed even though voltage modified. The voltage is modified. Not only voltage, winding connection is also modified. Earlier it was wave connection, now it is lap connection. Earlier it was wave connection, now it is lap connection. Okay, so speed has to be constant, N is constant. Overall conductors I am not disturbing, Z is constant, poles are constant. What are the only variables? Flux and parallel paths. Why parallel paths are changing? I am changing wave connection to lap connection, right? Voltage also modified, 480 240. That means the given condition will be satisfied only when phi 2 equal to phi 1. Second case flux and first case flux must be equal. Fluxes will be equal only when MMFs are equal. This is the given condition, guys. Case number 1. This is the given condition. In the given condition, the field MMF is equal to NF into 480 by RF. Therefore, in the second case also, MMF must be same. Then only I can say the given condition is satisfied. So I found that the MMF will be same only in first option. Only in first option, the MMF is same. In first option, two similar windings are connected in parallel. These two windings will have same resistance, okay, identical winding, right? This is RF, this is RF. Therefore, the current in this path is 240 by RF. Current in this path is 240 by another RF. 240 by RF. Like the two windings are. So, right. Next question. This is look at the options. Based on options, you have to understand it is MSQ question. The options are in square brackets. That means it is MSQ question. I'm very proud of all of you. Most of you are responding. Keep going there. Keep going. Whether question is easy or difficult, never give up. Try as much as you can. Whether you get the final answer or not, that is not so important. But how much effort you are putting, that is what you have to believe in. Your efforts are very important rather than the final results. You give your best. Okay, that is important. Okay, anyway, read the problem. A separately excited DC motor takes a current of I at speed n. What is the current at speed 3n using field control when output is constant, with voltage control when output is constant, with field control when torque is constant, with voltage control when torque is constant? So initially the speed was n. Next case the speed becomes 3n. That means speed is multiplied by 3. In the entire problem, there is no information about armature resistance. So you can neglect armature resistance here. Okay. Also, let's see what is the speed equation first of all. I have written in the previous example also. Speed is equal to voltage by Ka into phi. I am neglecting Ia Ra drop. Strictly speaking, minus Ia Ra will also be there. Now to change the speed, you have two techniques. One is voltage control. Another one is field control. Okay. So what is given? In the first case, speed is n. In the next case, speed is 3n. That means speed is multiplied by 3 times. So in the first case, which control is used? Field control is used. Field control means flux is modified. That means voltage is constant. So if I go with field control, indirectly flux is variable, voltage is constant. Then can I say speed is inversely proportional to flux? Look at the formula for flux. Voltage is constant, Ka is constant, speed is inversely proportional to flux. And what happens to speed here? N becomes 3n. Can I say speed will be multiplied by 3 times only when flux is divided by 3 times? Therefore, phi becomes phi by 3, then omega becomes 3 omega. Correct or not? So flux indirectly becomes phi by 3. But the question is not about flux, but we have to find out what is the current. What is the current in the second case? What is the current in the regular case? I. What is a new current? We all know current will always depend upon the type of load connected to the motor. What type of load is connected in the first option? Output is constant. By default, output constant means indirectly power is constant. So, given power is constant, what is the formula for power? Power is equal to torque into speed. Correct? What is the torque formula? Ka phi Ia into speed. Correct or not? Torque is equal to Ka phi Ia. Therefore, it is given power is constant. Okay. Flux becomes divided by 3. Phi becomes phi by 3. So what is the current? So according to this, current is inversely proportional to phi into omega. Are you understanding that? Ka constant, guys. Keep current here. Take phi and omega to the left side. So current is inversely proportional to phi and omega. Already what is omega and phi? Inversely proportional. Both will cancel. Therefore, Ia is constant. Are you understanding? Phi becomes divided by 3. Omega becomes multiplied by 3. Divided by 3, multiplied by 3. Both will cancel. Ia is constant. Ia is constant means what? In the second case also the current should be I only. This is all when power is constant. So therefore, in field control method, when power is constant, armature current is also constant. Armature current constant means what is the new current again? I. Rated current is I, the new current is also I when power is constant in field control method, therefore option A is correct. Okay. But there is another option with field control method. Field control method, when torque is constant. What if torque is a constant value? If torque is a constant value, what is the formula for torque? Ka phi into Ia. If torque is a constant value, Ka is a constant value, armature current is inversely proportional to flux. What happens to flux? Flux is divided by 3. If flux is divided by 3, can I say current will be multiplied by 3? Therefore, the new armature current will be 3 times of I. It is multiplied by 3. Therefore, the new armature current will be 3I. But in this, it was given I by 3. I by 3 is a wrong answer. Remember, this is a field control when torque is constant. Field control when a torque is constant, the new current must be 3 times of I, but in the question it was I by 3, therefore C is wrong answer. What about the remaining two? Remaining two questions are about voltage control. See, when I say voltage is controlled, can I say flux must be a constant value? Yes. So let's see voltage control method. Voltage control. Speed is equal to V by Ka phi. When you try to control the speed using voltage, flux must be constant. If a flux is a constant, the speed is directly proportional to voltage. And in the given question, n becomes 3n. That means the speed is multiplied by 3. So can I say according to this, speed can be multiplied by 3 times only when voltage is multiplied by 3 times because directly proportional. When voltage is multiplied by 3 times, the speed will also be multiplied by 3 times. Therefore, the new voltage was 3 into V. Now, what happens to current? So, first case, I would like to answer if power is a constant value. If power is constant, once again, power is equal to torque into speed. Torque formula, Ka phi Ia into speed. Power constant, Ka constant. Remember, in this method, flux is also constant, right? Flux is a constant value. Therefore, Ia is inversely proportional to speed. If Ia is inversely proportional to speed, what happens to speed? Speed is multiplied by 3 times. According to inverse proportionality, if speed is multiplied by 3 times, current will be divided by 3 times. Therefore, the new current will be equal to rated current by 3. This is if power is constant, voltage control method, the new current is I by 3. See, voltage control method, when power is constant, the current becomes I by 3, therefore B is a correct answer. Correct or not? B is a correct answer. What if torque is constant? Another question I have to answer. What if torque is constant? Okay, I don't have space. Okay, let me solve here only. If torque is constant, what is the formula for torque? Torque is equal to Ka phi into Ia. Torque is constant. In this question, flux is also constant because it's a voltage control method. Flux is constant. Torque constant, flux constant. That means what? Ia is constant. Ia is constant means the new current must be I. Again I. Okay. So this is voltage control method. When a torque is constant, the new current is I. Current is constant. Therefore, last option is also correct. That means, what are the correct answers now? A, B and D are the correct answers. C is the only wrong answer. A, B, D. It's a multiple select question, MSQ. Options are having square brackets. I should have mentioned that. I forgot it. But anyway, based on the options, you can understand it's a MSQ question. A, B, D are the correct questions. Correct answers. So one important observation, when armature resistance information was not given, you can neglect IARA drop. You can neglect IARA drop. Yes, A, B, D are the correct answers. Yes, Chakradhar, your answer is correct. Good. Shadow Monarch 314, your answer is also correct. Kavita, correct answer. A, B, D are the correct answer. Okay. All right. This is again speed control problem only. Okay. Now another simple question. Please read this problem. I thought I could complete the session in 2 hours, but let's see. We have another 2 questions after this. Okay. Read the problem. A series generator having an external characteristics which is a straight line through 0 to 50 volt at 200 ampere. And it is connected as a booster between a bus bar and a feeder of 0.3 ohm. Okay. Calculate the voltage between the far end of the feeder and the bus bar at a current of 160 ampere. This is indirectly the application of DC series generator. Application of DC series generator. Okay, let's see. A series generator having external, generally series generator will have rising voltage characteristics or drooping voltage characteristics. Rising voltage characteristics, right? Okay. Yes, that's why it is used as a voltage boosting circuit normally. And that actually the characteristics will be non-linear, but in this question it was given it is a straight line passing through 0. First of all, external characteristics are drawn between which parameters? External characteristics are drawn between terminal voltage versus line current or armature current. Both are same only in series generator. And it is given a straight line passing through origin. Usually it will start with residual voltage and then will increase in a non-linear fashion. But in the question, maybe an ideal magnetic circuit is considered or saturation is neglected. So it's a linear line. And it is reaching 50 volt at 200 ampere. Okay. So if the current reaches to 200 ampere, then this generator can generate 50 volt. Okay. This is the given characteristics, guys. Now, this generator is connected as a booster between a bus bar and a feeder. That feeder is having a 0.3 ohms. So the observation is, imagine this is the bus bar voltage, the bus bar terminal. And between the bus bar and there is a feeder. But that feeder is having an internal resistance of 0.3 ohm. Okay, there is a feeder and there is a bus bar. If you connect this bus bar directly to the feeder, what will happen? Whenever current flows, voltage will drop across this resistance and feeder will receive less voltage. Got it? Feeder will receive less voltage. At what current we are asked to find out the voltage drop? 160 ampere. Okay, for example, if 160 ampere goes here, then how much will be the voltage drop? The voltage drop would have been 160 into 0.3, how much? 48 volt drop would have been there. Okay, that means if you give 100 volt to the bus bar, then only 48 will be received by the feeder. 48, sorry, only 52 will be received by the feeder. 48 volt drop is there. Therefore, to reduce that drop and to boost the voltage, we will connect a series generator now. So now what I am doing, between bus bar and feeder, this is the feeder voltage, feeder resistance 0.3. Between these two, rather than connecting them directly, I am using a series generator. So imagine this is the voltage generated by series generator. Got it? Now the question is, how much voltage this series generator will generate? Of course, the series generator will have its internal resistance, but in the question, internal resistance of the generator was not given, right? Field resistance, armature resistance, nothing was given, so I am neglecting it. Only the generated EMF I am taking. And we are asked to find out this voltage at what current? When it is 160 ampere. When the bus bar and feeder were carrying 160 ampere. But I know the generated EMF of the generator at 200 ampere. If the current is 200 ampere, my machine would have generated 50 volt. But if the current is 160 ampere, how much current it will generate? Sorry, how much voltage it will generate? An unknown value. But is it looking like a straight line passing through origin? That means y is equal to mx. Therefore, you can easily find out what is this unknown voltage. Okay, yes, how much? So that unknown voltage would have been, let us assume it is Eg. This unknown voltage is nothing but Eg. So you can apply y is equal to mx. So 50 by Eg is equal to 200 by 160. So what is Eg at 160 ampere? That 50 will cancel 4 times. So 160 by 4, is it not 40 volt? So therefore, if the machine can generate 50 volt at 200 ampere, it will generate 40 volt at 160 ampere. So therefore, our machine voltage was equal to 40 volt. Okay. So now tell me, what is the overall voltage drop? Current is flowing this way from bus bar to feeder. If the current was flowing this way, 160 ampere, so first you will have generated EMF and then voltage drop. Okay, so 40, this is the boosted voltage, the voltage was boosted, minus what is the voltage drop here? 160 into 0.3. Okay, so how much? This is when the current was flowing from bus bar to feeder. That means this drop is from bus bar to feeder. VB minus VF is the drop here in this circuit. Okay, tell me how much is the drop? Take a calculator and let me know. 8 volt, correct. So 40 minus 160 into 0.3. Drop is minus 8. But this is from where? Bus bar to feeder or feeder to bus bar? Bus bar to feeder, according to current direction. Then what about feeder to bus bar? It will be plus 8 volt. They are asking from bus bar to feeder or feeder to bus bar. Voltage between far end of the feeder and bus bar. So I need feeder to bus bar. Then it will be plus 8. That means you see the difference between before connecting a series generator, what is the overall voltage drop? 48 volt drop is there. But after connecting series generator, 8 volt drop is there. That too plus 8 or minus 8. Minus 8 means the voltage is actually boosted or whatever. So 48 volt drop is reduced to 8 volt drop. Voltage drop reduced, that is an advantage or disadvantage? Advantage, right? That is why in DC circuits, at intermediate stages, series generator will be connected. This is a boosting circuit, right? Series generator is used as a voltage booster. Okay. This is before connecting a series generator. If bus bar and feeder were directly connected, you would have 48 volt drop is there, but here it is 8 volt. Right. This is a regular question only, not so difficult. Please go through it. Okay. Okay, I'm expecting you answer this question. Two conditions are given. One is no load condition, another one is loaded condition. See, a 250 volt shunt motor on no load runs at 1000 rpm and takes 5 ampere current. No load condition is initially given. The total armature and shunt field resistances are 0.2 ohm and 250 ohm. The speed in rpm when loaded and taking a current of 50 ampere if armature reaction weakens the field by 3%. Okay, so initially the machine is under no load condition, so calculate back EMF under no load condition. Next, the machine is under loaded condition, so find out the new back EMF. You will get easily what is the new speed. Okay, so let's take case number 1, which is the no load condition. So initially the motor is under no load condition. What is the terminal voltage? The terminal voltage of the motor was 250 volt. What is the total current drawn from the source? It was 5 ampere. Remember, armature resistance is given, field resistance is also given. So I have to consider both of them. I cannot neglect this time. Out of this 5, how much will go to the field circuit? It's a shunt motor. In shunt motor, what is the formula for field current? Vt by Rf. Vt was 250, field resistance was 250. Therefore, 1 ampere will go to field. If 1 ampere goes to field, how much will go to armature? Therefore, the armature current would have been equal to line current minus field current. 5 minus 1, 4 ampere will go to armature circuit. The moment you know armature current, find out what is the back EMF. So what is the formula for back EMF? Back EMF is equal to Vt minus Ia into Ra. Vt was 250. Armature current was 4. What is armature resistance? 0.2. So it was 249.2 volt. That is the back EMF in the first case, which is nothing but a no load condition. Now let's move to the second case, which is the loaded condition. During a loaded condition, once again the terminal voltage was 250 only, but this time the machine will draw more current because the load is connected. How much current was drawn by motor? Taking 50 ampere this time. Okay, so the current was 50. Out of that, how much will go to the field? 1 ampere will go. Field current does not change. Why? It's a shunt motor. In a shunt motor, field current will be constant unless you add some extra resistance in field. So no change in field current. Then how much will go to armature? 49 ampere will go to armature, correct? Out of 50, 1 goes to field, remaining current 49 will go to armature. So calculate the new back EMF. What is the new back EMF? Vt minus Ia into Ra. Vt doesn't change, same 250, but armature current was a 49. If it is a 50, it would have been 10. Approximately 240, right? Exactly speaking, more than 240. 240.8 probably, right? Okay, 240.8 or 240.2, whatever. So that is the new back EMF. So the moment I know what is the back EMF, I can easily find out what is the new speed, because we know back EMF is equal to Ka phi into omega, and flux is a constant, don't forget that. Okay, why flux is a constant value? Because the field current remains the same. So back EMF is directly proportional to speed, correct? So EB1 divided by EB2 is equal to N1 divided by N2. What is the back EMF in the first case? 249.2. What is the back EMF in the second case? 240.8. What is the speed in the first case? 1000. What is the speed in the second case? We have to answer, that is the, okay, you'll get the new speed. Definitely the speed will decrease because the load is increased, right? Okay. Shunt motor will offer drooping speed characteristics. So whenever load increases, speed will decrease. Clear? All right. Yes, what is answer? Yeah, 993.6. All of you get the same answer? Answer up to 2 decimal places. So we need exact answer. 993.6. All of you got the same? 993.6. Okay. All right. Fine. Fine. So read this problem. This is a difficult question, a 2 marks model. It's a 2 marks model, a slightly difficult question. First read the problem, everybody. Understand what was the data given. Understand the given question. Yes, read the problem. The following data refer to a direct current shunt machine. Total armature resistance 0.3 ohm. Field resistance 40 ohm. Open circuit characteristics. You remember shunt machine open circuit characteristics. Open circuit characteristics are drawn between induced EMF and field current. Okay, look at that. Open circuit characteristics at 1000 RPM is such that the field current is 5 ampere for an EMF of 220 volt, 4 ampere for an EMF of 200 volt. Neglecting armature reaction, what is the external resistance required as a shunt regulator to obtain a speed of 1000 RPM when running as a motor on 220 volt supply at the full load armature current of 35 ampere? Okay. So quite an interesting question. First, you need to understand the open circuit characteristics given there. Okay, everybody please understand open circuit characteristics. Open circuit characteristics are drawn between field current on x-axis, induced EMF on y-axis. Okay, normally these characteristics will start with residual voltage. Of course, if residual voltage is neglected, then it will start with origin. Otherwise, they will start with residual voltage. And this is how the graph will be. Usually, we will operate the machine in the linear zone only. We won't let the machine to saturate, because in the saturation zone, large amount of field currents are required. So according to the question, when field current is 5 ampere, EMF is equal to 220 volt. Let's say this is the operating point. When field current is 5 ampere, the EMF was equal to 220 volt. Okay. Next, if the field current is 4 ampere, EMF would have been reduced to 200. For example, if the field current is reduced to 4 ampere, the EMF would have been reduced to 200 volt. Okay, so that you can understand what is the slope of this graph, right? Okay, now this is an open circuit graph that was given. This is all when machine was rotating at how much speed? 1000 rpm. This is all when the machine was rotating at 1000 rpm. Okay, clear? Now neglect the armature reaction. What is the external resistance I have to add in the field circuit so that machine will rotate at 1000 rpm when running as a motor drawing 35 ampere. So now the machine is operating as a motor. When machine is operating as a motor, supplied from 220 volt, rotating at 1000 rpm, drawing an armature current of 35 ampere. Correct? This is the motor details. Motor is also rotating at 1000 rpm, 220 volt supply, armature current of 35 ampere. Now what I will do is that I will find out back EMF from this information. What is the back EMF of the motor? Vt minus Ia Ra. Vt was 220, armature current was 35. What is armature resistance? Look at this, 0.3 ohm, right? 0.3 ohm. So how much is this? Let me use my calculator. Where is it? Can somebody tell me in the chat box what is the back EMF value? 220 minus 35 into 0.3. 209.5 I am getting. 209.5. This is the induced EMF now. Can I say back EMF is nothing but induced EMF only? Now the point is, this is all when the speed is how much? 1000 rpm. Even the OCC graph is also when the speed is 1000. Now tell me, yes, according to this OCC graph, this 209.5 volt can be obtained at what field current? See, 220 volt, this is induced EMF only, indirectly back EMF. 220 volt I can get at 5 ampere field current. 200 volt I can get at 4 ampere field current. Then 209.5, almost 210. Can I say 209.5 will be in between these two? Yes or not? It will be in between these two. So at what field current I will get that 209.5? This is, I don't have space, let me write 209.5. Can you estimate according to the given graph? At what field current I will get that 209.5? Definitely between 4 and 5, but I need exact answer. Come on. If 5 ampere can give you 220 volt, 4 ampere can give you 200 volt, then what current will give you 209.5 volt? Come on guys. 4.76. I think it is correct. Yes, Shadow Monarch. I don't know your exact name, but it looks interesting. Shadow Monarch. Okay, 209.5 minus 160 by 10. 4.76. Is it correct? Everybody got the same? Come on, participate, guys. I gave you a linear relation at 200 at 5 ampere current, EMF was 220. At 4 ampere current, EMF was 200. Then at what current 209.5 will come? That's the question. Right or not? It's like y is equal to mx or y is equal to mx plus c equation. Come on, I am expecting answers from you. Okay. See, this is how open circuit graph will be. IF and induced EMF. If residual magnetism is neglected, then it will start from origin. But if residual voltage is there, it will start from some finite value. This is how the graph will be. If you take only linear portion, it is like y is equal to mx plus c equation. At 5 ampere field current, the voltage was 220. At 4 ampere field current, the voltage was 200. What is the slope of this graph? Slope, change in y-axis by change in x-axis. What is the slope? M. So I can calculate slope m is equal to dy by dx. See, what is the change in y-axis? Is it not 20? 20. And what is the change in x-axis? 4 to 5, it is 1. Therefore, the slope is equal to 20. Okay. If slope is equal to 20, I can write this equation as the y is equal to mx plus c. This is nothing but c, guys, the constant c. Slope of the curve. Okay. Now you see, this is y-axis, this is x-axis. Y-axis will reach 200. Okay. When x-axis is 4 ampere. So can you tell me what is a constant c there? So y is equal to mx plus c. Y-axis value will reach 200. Slope is 20. When x-axis is 4 ampere, please see that x-axis is the field current, 4 ampere. That means what is a C? Is it not 120 volt? Yes. Therefore, this is 120 volt indirectly. Is it not voltage due to residual magnetism? Yes. That is 120. Now, I need at what field current 209.5 will come? Let's say that unknown field current is IF. At what field current 209.5 will come? According to this same equation, y is equal to mx plus c. What is the y-axis value now? 209.5. What is the slope? 20. Yet what is x-axis value? I don't know. That is what I have to find out, right? At what field current that will come? That is IF. C will not change, right? 120. So now you tell me at what field current that 209.5 will come? Correct? Yes. So 209.5 minus 120 by 20. 4.475. Yes, 4.475. 4.475. Yes, this is the field current. This is the field current. Okay. What is the formula for field current? We know field current is equal to, it's a shunt motor, right? It's a shunt motor, shunt machine. What is the formula for field current? Vt by not only RF, guys, we are adding extra resistance. Please understand. Okay, what is the answer we have to find? What is the external resistance required in shunt field regulator? What is the extra resistance you need? If you don't add extra resistance, current will not become 4.475. A different current will come. So now 4.475 is equal to, what is the supply voltage? 220 by, what is the field resistance? Field resistance is 40, right? So field resistance is 40 plus what is the extra resistance? For example, if you don't add this extra resistance, you would have get field current more than 5 ampere, 5.5 you will get. But I need 4.475 only. So that what is the extra resistance I need? Come on, tell me the answer. Do you understand? If I don't add that extra resistance, field current would have been 5.5. But to get the exact speed and to match the information, I need field current must be 4.475. So what is the extra resistance I have to add? Come on. 9.162. We need up to how many decimals places? 2 decimal places. 9.16. Correct answer, everybody? 9.16. Correct. 9.16 is the correct answer. So anywhere between 9.1 to 9.2 will be treated as correct answer. So the extra resistance required is 9.16. Okay. That's all, guys. So with this, I would like to complete this session. It's already 10:20. So I would like to complete the session here today. Please don't worry even if you are unable to answer these questions, because I discussed some difficult models. All right. And before concluding the session, I would like to mention once again, we are conducting an all India level free mock examination before the GATE exam on January 10th. Okay, it is free of cost. Anybody who are aiming for GATE 2026 examination, you can register for this mock examination. Okay, so in the link in the description, the link is available to register for this mock examination. It is an online examination. Okay, so you can attempt it from your home, and we are preparing questions on par with GATE examination. Okay, so this will definitely help you to assess yourself before the GATE examination. So we are conducting on January 10th, and we have hardly around 8 days left. So after attempting this exam, you have another month left, right? Your exam will be on February 14th or 15th. So you will have at least 1 month time, so that in case if you make any mistakes, you can fix them. Okay, you can revise the things and you can make necessary changes to your revision and practice. All right. So I'll come up with more number of sessions like this on other machines also. Okay, but this year I just wanted to discuss only difficult questions. All right, if you are expecting easy questions, you need not to tune to these live sessions. I only discuss difficult questions this year. That is my motto. A new year resolution: discuss only difficult questions in YouTube. Okay. All right, I appreciate everybody who responded with quick answers. So really wonderful to see all of you responding to the questions. All right, so I'm signing off. All right, so good night everyone, and once again wish you a very happy new year. Hope this year will give you a lot of success, happiness and good health. Okay, thank you.